First, we'll review specific heat capacity and latent heat. Specific heat capacity is the number you need so you can predict how much heat it will take to warm up an object. What you do is to figure out that quantity of heat, which we call Q, you take the mass of the object that you're warming up, you multiply by the value of C, which we look up in a table, and then you multiply by the temperature change that you're after. Now, notice that the value of Q can be positive or negative. If you're increasing the temperature, delta T is positive, and then Q is a positive number. But you can also be, of course, taking heat away from an object, lowering its temperature, and then in that case, Q is negative. So Q has a sign to it, plus or minus. Q is positive when the heat goes in, negative when heat goes out, and the temperature drops. C is specific heat capacity. It's specific because it's the heat needed per kilogram of substance, specifically per kilogram what's needed. Also notice that although we, generally speaking, should always be working with the Kelvin scale, in specific heat problems, the only thing that appears is a temperature difference. And if the temperature increases by 5 Celsius, isn't that also an increase by 5 Kelvin? Yes, because the intervals on the Celsius and Kelvin scale are identical. So in these kind of problems, you can use either Celsius or Kelvin scale. The delta T values are the same. Now, that's if when you put heat in, the temperature of the object rises. In some cases, when you put heat into something, the temperature doesn't go up. What's happening is it's changing phase. The heat that you're putting in is not going into warming it, but into creating the like the vapor, for example. When you boil water, the temperature of the water is not going up. It stays at 100 Celsius until all the water has boiled away, and then you're warming up steam after that point. So to calculate the Q that's needed in a phase change, there's no delta T involved, it's a delta M. You're creating a certain amount of steam, that's the delta M value, the steam being produced, and you multiply by a number which is called the latent heat, L. So in this case, again, Q can be positive or negative. Delta M refers to the mass of the higher phase which is produced. So for example, if you create steam, delta M is positive, you're generating steam, and Q is positive, heat goes in. However, if you're condensing steam into water, then you say delta M is negative and Q is negative. You have to take heat out. You have to cool off the steam in order to make it condense. So at this stage, we have to use a table to look up the values of C and L for different materials, aluminum, iron, gold, and so on. And then our different L values for latent heat. We use a table to look it up. I'll just mention that in the future, in a future chapter, we'll be able to predict the value of C from basic principles. Now let's look at an example. A bullet is fired into a large block of ice. The bullet is warm when it's fired and the ice is at 0. What quantity of ice melts? So there are 2 factors which determine how much ice melts. First of all, the bullet loses kinetic energy. That energy goes into the ice and melts some of the ice. Also, don't forget here, the bullet is warm. So some heat flows out of the bullet, and that also melts some ice as well. In other words, what I'll do is I'll set the change in kinetic energy of the bullet plus the heat which it gives into the ice, M bullet, heat capacity of the bullet times delta T. This accounts for the total energy lost by the bullet, and I'll set that equal to the heat which melts the ice, delta ML. That's delta M ice times L ice. Okay, now we should be a little careful here because actually delta K is a negative number. The bullet loses its kinetic energy. So really what I mean is the absolute value of that. And likewise, the bullet actually cools off. So its final temperature is actually lower than the initial. So delta T is really negative. So really what I want is absolute value around that. Also, the ice melts. So I should just think about the sign of this. Delta M is positive because you're going into the higher phase. You're generating water from ice. So delta M is positive, and I'm good with the signs then in the equation. So this means that I just have to figure out the delta K. Delta K is the 1/2 mv squared, mass of the bullet, times its speed squared. It loses, I assume, all of its speed in the impact. Why? Well, because it's a very large block of ice. It's very large, so when it hits the ice, there's very little recoil that occurs. If there were any recoil, I'd have to account for the recoil, which we'll do in the next question. But the point is, it's now plug and chug. I can now solve for delta M. And I find that it is 0.142 grams. To get the number, I had to look up the value of C for lead. In the next question, two bullets are going to hit each other. Two lead bullets hit each other, and I want to figure out, is it possible for the bullets to actually melt when they collide head on? In this case, I can't ignore the recoil because they're going to hit together. They're still going to be moving after the impact, and so we'll have to account for that. The bullets are going to make a head-on collision, and I need to figure out their possible recoil speed afterwards. We do that using conservation of momentum. So it's a collision. I've got bullet number 1, and it's moving to the right. Bullet number 2, slightly different mass. It has a higher speed, moving to the left. So I'll call this one M1, moving at velocity U1, and this one's M2, moving at velocity U2. Actually, let me call it the speed because I want to make sure to show the sign. So they're going to hit together, and they're going to merge into one blob after the impact. They're going to collide together, but they're still going to be moving after the impact. Our job is to figure out what that speed is after the impact. I'll call it v. It matters what that speed is at after the impact because you see all of the kinetic energy the bullets have at the beginning does not get converted into heat. Only some fraction of it does. Some of it is trapped in the motion of them together afterwards. We call that the energy trapped in the center of mass motion. So to figure out what the speed is afterwards, of course, I need to use momentum conservation. So I'll take M1, U1, and then I'm just letting these be the speeds. So I'll take minus M2, U2, just to remind us that this one's moving to the left. So I got to plug in a minus sign. And then I set that equal to the total momentum afterwards, M1 plus M2, times the unknown velocity afterwards. So again, I would just plug in positive numbers for U1 and 2. The minus sign accounts for the direction. And I find that the speed afterwards, it still has a speed. It's 21.1 meters per second. That's how fast the lead blob is moving after the impact. Okay, so like for the previous one, melting the ice, I need to set the change in kinetic energy equal to the heat that goes into melting the lead. But I just have to be extra careful because not all the kinetic energy turns into heat. What I have to do is calculate the kinetic energy initial, which is just 1/2 m1 v1 squared, or u1 I called it, plus 1/2 m2 u2 squared. The total kinetic beforehand, the kinetic energy final is not 0, it's equal to 1/2 m1 plus 2 multiplied by v squared, the speed we just found. And what I really care about is the change in kinetic energy of the bullets. The change in kinetic energy of the bullets, the value I have is minus 980 joules. Again, not all of it is lost. Some of it remains in the recoil afterwards. Okay, so I take that 980 joules and I have to figure out how much lead can that melt. So what I'll first do is, the bullets are not originally at their melting point. First, some of the heat that's generated in the impact, some of this 980 joules, it goes into warming up the bullets to their melting point, and then I got to figure out how much is left over to do the melting. So first I'll write down the heat to reach the melting point. That's just an MC delta T. M1 plus 2, because I'm melting both of them. C for lead, MC delta T. The delta T that's needed is 297.3 because I have to go from 30 up to 327. So just to be sure, I'll write it in 327.3 minus 30. That's the delta T value that we're interested in. I plug in the total mass and the C value. I get a heat needed, which is 771 joules. So 980 are generated in the impact. That's more than enough to warm up both bullets to their melting point. So that means after the impact, they're 327 degrees. How much heat is left to melt? Just the difference. The heat left to melt the bullets is the difference in these two, which is 209 joules. And so now I need to figure how much lead can you melt with 209 joules of energy. So it's a delta ML problem. Delta M, I said delta M. This is the mass of molten lead produced. It'll be equal to 209 joules divided by L for lead. It comes out to be 8.5 grams, 8.54 grams, which is like roughly half of the total amount. So it's a significant amount of energy is there. Even though not all of it can go into melting it, there's enough to melt a lot of it. Calorimetry is the science of studying heat, and the typical examples are you mix two things together at different temperatures, and you want to know what's the final stage that's reached. Like, does it boil all the water away or what? For instance, 100 grams of iron at a high temperature is cooled by dropping it into water at 20 Celsius. What's the final temperature of the system, and how much water ultimately is vaporized? So the essence of these problems is that whatever heat comes out of the iron, the quantity of heat which leaves the iron is the same quantity of heat which enters the water. So essentially, I set up an equation which says Q for the iron equals Q for the water, and it lets me solve for the amount of water which is vaporized. Because the Q for the water is going to involve a delta ml, we're going to solve for delta m. That's the essence of it, but there's kind of an art to it. You have to calculate some preliminary numbers to see where the problem's headed. So in this case, what I'll do is figure out how much heat is given off. Well, actually, let's first figure out how much heat it takes up to warm the water to 100 degrees. The heat to warm the water to its boiling point. That is from 20 up to 100 degrees Celsius. Let's figure that out first. This will be mass of water, C for water, times delta T, which will be 80 Celsius. Now, in these problems, I'm going to work in calories for the unit of heat. It's convenient because the specific heat of water is 1 calorie per gram per degree. If you do it in joules, and it's like 4.19, that's fine too. It's just, for me, it's easier to use calories in these, but it's totally your choice. It won't affect the answer, of course. Okay, so we've got 75 grams of water times 1 times 80. It gives me 6,000 calories that are needed. Okay, that'll get the water up to its boiling point. If as the iron cools down to 100 degrees, how much energy is it going to give off? So here's the cooling the iron from 745 degrees down to 100. Let's see how much that takes. That's mass of iron, specific heat of iron, times a temperature drop of 645 degrees. So we've got 100 grams of iron. We have to look up C for iron. It's 0.11 calories per gram per degree. So this comes out to be 7,095 calories. Okay, so I have these two numbers. The reason I needed to look at both of those numbers is the iron's going to give off over 7,000 calories as it cools off. That's more than enough to warm the water up to its boiling point. There's an extra 1,095 calories from the iron, which will be used to vaporize, to boil some of the water. It takes a massive amount of heat to boil all 75 grams of water, but the extra 1,095, it will be enough to boil some of the water. So what I'll do is I'll set the excess, 1,095 calories, equal to delta ml. That's delta m of the steam that's going to be generated times the latent heat. And that gives me a delta m value. It comes out to be about 2 grams. L is 540 calories per gram for water, the vaporized water. So it comes out to be about 2 grams, 2.03 grams. Okay. It might be useful for me to show it a little more systematically. What I'm really doing here is setting the heat that comes out of the iron equal to the heat which enters the water. So let me write it that way. This is one way to think about it. Another maybe more systematic way is to set the heat which leaves the iron, that is mass of iron, C iron, times 645 degrees. I set that equal to the heat which enters the water, which is first the warming part of the water, mc delta T, plus the delta ml part of it. Okay. Notice carefully, this is mc delta T for the iron. Now, delta T for the iron is actually negative because it's cooling. So this is really the absolute value of Q. It's the amount of Q which leaves the iron. And I set that equal to the heat which enters the water. It's the difference between this left side and this term here, which gives me the 1095, which I set equal to delta ml. Same thing. That's just systematically what's really going on here. Here's steam and ice mixed up together. We've got 85.5 grams of ice and 10.8 grams of steam combined. So like before, it's a problem where we have steam. Heat's going to come out of the steam. The same heat that leaves the steam enters the ice. It's going to melt some of the ice. How much is going to melt? What's the final temperature of the system? Actually, the question is determine the amount of steam which condenses and the final temperature of the system. Remember that when two things are combined together, they're going to reach a common temperature at the end. The final state of things, what we call thermal equilibrium, can't have different parts at different temperatures. The heat's going to keep flowing until the temperatures are equalized. Okay, so like before, we have to look at some preliminary numbers to see where the problem's headed. So the first thing I'll calculate is the heat from the steam as it condenses. How much heat does it take to condense the steam? So that's a delta ml. I would take 10.8 grams delta M for the steam times the heat of vaporization. Delta M is, I want to know how much it would take to condense all the steam. So I just need to see the number and see what it is. So it's 10.8 grams of steam, the L value 540, it gives me 5,832 calories. Okay, let's compare that against the heat needed to melt all the ice, all 85 grams of it. That's a delta ml, delta M ice, L for the ice. That's 85.5 grams. The L for melting, the heat of fusion, is 79.8. So this number comes out to be 6823 calories. That means, imagine what happens here. Suppose all this heat leaves the steam and goes into the ice. It is not enough to melt all of the ice. So all the steam condenses. You now have hot water. You have 100-degree water in combination with some 0-degree ice water. You're roughly 1,000 calories shy of enough water to completely melt the ice. But the point is, at this stage, I've got hot water from the condensed steam and I've got cold ice water together. The process is not done. What's going to happen is the hot water is going to continue to cool off and melt more of the ice and warm up that melted ice water, and they're going to reach some final temperature somewhere between 0 and 100 degrees Celsius. So let's see what we have here then. I'm going to do a Q equals Q equation. This is going to be the heat which leaves the steam plus the heat which leaves the hot water from the condensed steam. That's an MC delta T. That's just mass of the steam. Now it's not in the form of hot water, but it's the full 10.8 grams. C, it's now water, so I would use C for water. And the delta T. I don't know what the final temperature is. T is unknown, the final temperature T. So I just call it T, 100 minus T. That's the MC delta T for the condensed steam. I set that equal to the heat that goes into the melting the ice and then warming up the ice the cold water. So that's the delta M ice, L ice, heat of fusion, plus the MC delta T. It's now melted ice, which is water. So it's mass of the ice times C for water times the delta T for the cold water. It started at 0 and ends at some unknown final temperature T. Okay, so again, this is just the left side is the heat which leaves the steam as it condenses and then cools off to its final T. The right-hand side is equal to it. It's the same amount of heat which enters the ice, melting the ice, and then warming up the cold water up to a final temperature T. So it's an algebra problem to now solve for T. You can just do it algebraically, or good practice, use your calculator, y1 equals the left side, y2 equals the right side, and have it numerically find the value of T. It comes out to be 1.13 degrees Celsius. So the steam fully melted the ice. All the steam condenses. We figured that out at the beginning. All the steam fully condenses, and in the end, the final temperature is about 1 degree. In this question, we have 50 grams of super cold ice. It's cooled below 0. It's added to a bunch of water in an aluminum calorimeter, a container that holds the experiment. The water and the aluminum are initially at 25 Celsius. Determine the final temperature of the system. Okay, so like before, I calculated some preliminary things. First, I want to figure out how much it would take to basically melt all the ice. Okay, so I'll look at, of course, to melt this ice, I first have to warm it and then melt it because it's not already at the melting point. So I have to warm it up 50 degrees up to 0 and then melt it. And how much heat will that take? Well, that would be mass of ice times the specific heat for ice, which is about a half a calorie, times delta T, which would be 50 degrees, plus the melting part of it, that's the mass of the ice times L, the heat of fusion, about 80 calories. That comes out to be a total, which is approximately 5,000 calories. 5,200 something calories. Okay, to warm and melt the ice would take that much. Now, how much heat is there in the water and the aluminum? Because if there's more than enough, more than 5,000, then it not only is it going to melt the ice, but it's going to warm up the melted ice water above 0. So let's just check that. The heat that's involved in cooling the water and the aluminum from let's say 25 down to 0. Like just suppose if you took the heat out of the water and the aluminum to cool it down to 0, how much would that give? So let's see. I would take the mass of the water, C for water. The delta T would be 25, plus the mass of the aluminum times specific heat for aluminum, which is about 0.2, times 25 degrees. And, well, that's about 13,000. When you plug in the masses and everything else, it comes out to be about 13,000 calories. Way more than enough, right? Way more than enough to, so what this means is when the ice, the super cold ice, is put into contact with the water and aluminum, the aluminum gives a bunch of heat into the ice, and it only takes 5,000 to completely melt all that super cold ice. The punchline here is that the final state of the system is more than enough from the water and the aluminum to melt the ice and even warm it up further than that. So what this is telling me is the final temperature of the system, all the ice is going to melt. All the ice melts, and there's so much heat available in the water and the aluminum that the final temp is going to be something, above zero. So it's now a problem to solve for that final temperature. What I'll do is I'll take the 5,000 calories, that's from the warming and melting the ice, plus now warming the ice water, it's the mass of the ice times the specific heat of water times the delta T. I don't know the T value, but it warms up from 0 to some final temperature T. That's the heat which enters the ice and the ice water, set it equal to the heat which leaves the water and the aluminum. It's not 25 degrees because it doesn't fully cool down to 0. So it's M water times C water multiplied by the delta T. It's 25 minus T. T is not 0. Plus the aluminum. Algebra problem now, solve for the temperature. I find the final temperature of the system is about 14 degrees. I have 14.3 degrees Celsius. Here we've got a piston which has a heater in the base. The heater boils water and the steam pushes the piston upwards. How can we figure out how fast the piston is rising? Now, there are two stages to the problem. In the first stage, there's still some water left, and we want to figure out how fast it's rising then, when there's water that's present. Then in the second stage, what about when all the water is boiled away and it's all just steam inside the container? Regardless of which stage you're in either case, the force of the steam is the same. Don't think that the steam becomes super pressurized or something as it gets hotter and hotter. That's not true. The steam, no matter what's going on here, the steam is just supporting the external atmospheric pressure and the weight of the piston. So in both cases, we need to remember here that the force from the steam, or let's say the pressure, P, the pressure of the steam is the same no matter what's going on here. It's just staying equal to atmospheric pressure, P0, plus the pressure from the weight, which is mg over the area. Or in other words, the force from the steam is just equal to the atmospheric pressure force plus the weight of the piston. That is not changing even as the heat goes into the steam. Okay, that's crucial to notice. Another important thing to notice here is that we're interested in how fast the piston's rising as it makes room for the steam. So the thing to notice here is the volume of the steam is related to the height. V, the volume of the steam, is just the area of the piston multiplied by Y. Y is the height of steam that's present. We'll need that in the ideal gas law, so we can relate the ideal gas law to the how high the piston is rising, how fast it's rising. Okay, so let's look in part A. We've already established that the pressure is staying constant no matter what's going on here. So what is changing? Well, pressure is staying constant, but in part A, you're generating steam. Steam is being produced. N is increasing. The number of moles of gas, steam, is increasing. Clearly, as the number of moles of steam increase, that requires more space for it, and it's going to be related to how fast the piston's going up. Okay, so the crux here is going to be to figure out what rate is the steam being produced. Is there a way to figure out as heat goes into something how much steam is being made? Sure, that's just Q equals ml. Q equals ml. actually delta ml. What I care about is the rate at which it's being produced. So I would take a time derivative, dq dt is just the rate at which the steam is being produced, the kilograms per second, multiplied by the heat of vaporization. So this is at the heart of the problem. Now since I know dq dt, it's 100 watts. That's the rate, dq dt, joules per second. It's 100 watts. Now I know how many kilograms per second of steam are being made, and I'll be able to use that to figure out how fast the piston is rising upwards. But first, I need to relate the mass per second to the number of moles per second, because the ideal gas law involves number of moles. That's easy to do. You see, I can use molar mass. The number of moles is the number of moles of something is equal to what mass you have of it divided by the mass per mole, capital M. That's molar mass for steam. M is about 18 grams per mole. That's how heavy the molecules are. 18 grams per mole. Okay, so I can use that to, instead of having dm dt, I can write it in terms of dn dt, the number of moles per second. So this is just the grams per mole multiplied by the number of moles per second times L. Now we're on our way. Now I know how many moles of steam are being produced per second, and I can relate that, because of the ideal gas law, to how fast it's rising. Because you see PV is equal to nRT. So if I know how many moles per second are being produced, I know how much volume per second is being made, and that's related to how fast it's going up. So what I should do is take, because I need to put it in terms of rates. So I take the time derivative of the ideal gas law. I have to know what things are constant when you take a derivative. The pressure stays constant in this case. So I'll have P dV dt. The temperature stays constant too, because you're just boiling water. As water boils, temperature doesn't rise. So T is constant. Of course, R is a constant. So on the right side, I have dN dt times R times the temperature, 100 degrees Celsius. So I have to use Kelvin. Okay, now we're on our way, because dV dt is just area times the velocity. So this is pressure times area times the velocity of the piston's rising. I'm calling it U. I don't want to write V, it looks like volume. And then on the right side, I have a dN dt, which is known from how much heat's flowing in. So dN dt is 100 watts divided by molar mass of steam times L. And that's that times R times the temperature. And that's it. Now I can predict the speed. The speed is going to be 100 watts. Now notice also that P times the area is just F, the force of the steam. So that's 100 watts times RT divided by molar mass times L times the force of the piston. Force of the piston is just from the pressure plus the weight of the piston. It gives me a number of like 4 millimeters per second, 4.2 millimeters per second. Okay. Now what about part B? In part B, it's very similar, except in part B, all the water has now been boiled away, and now the heat, the 100 watts of heat, are going directly into the steam, and now the steam's actually warming up. So in part B, it's not that the number of moles are changing, it's the temperature of the gas which is changing. So in part B, two differences. Now it's not Q equals ml. It's now Q equals mc delta T. So I have dq dt. M is not changing. All the steam is just still there. Mass of the steam, specific heat of steam, and now it's the change in temperature with time. This is Q equals mcat, but as a rate. dq dt is still 100 watts. And then the second difference is that, well, PV equals nRT. Now it's not the number of moles which change, it's the temperature which changes with time. So I'll have PA times the speed is equal to NR times the rate at which the temperature changes. So 100 watts determines how fast the temperature rises. I plug that in over here for the rate at which the temperature goes up. I solve for the speed. In this case, the speed comes out to be NR 100 watts times R divided by M, the molar mass, times the specific heat of steam multiplied by that force. Notice in this case, you get mass divided by the number of moles, which just gives you the molar mass, just capital M. I get a speed in this case. It comes out to be 12.7 millimeters per second.